Hi everyone, welcome back to the channel. So Intel has released a new quantum chip. It's called the Tunnel Falls Quantum Research Chip, and this is unsurprisingly based on their silicon-based technologies. It's a 12 silicon spin qubit chip, and it's like a research-grade chip that is intended for the research community. So it's not really a chip that you can go out and buy and plug into your computer as such. It is something where they collaborate with various places, and so they've been collaborating with places like Sandia National Labs and University of Delft and other places. So what we're going to do today is we're going to check out the performance of this chip, and let's see whether this chip lives up to this kind of Intel's name as obviously a super powerhouse in terms of classical computing. And so let's see whether they can transfer it onto the area of quantum computing. So just diving into the press release, there's not really a lot of detail about what actually this chip really entails. All they tell you is pretty much this one paragraph that they have. And so let's just at least have a look at this paragraph to see what kind of information we can get out of this release. So it says Tunnel Falls is Intel's first silicon spin qubit device released to the research community. So it's fabricated on 300mm wafers in the D1 fabrication facility. So 300mm wafers, that means these are these kind of wafers that you typically see in terms of these semiconductor fabrication kind of places. This D1 fabrication facility, I thought I was supposed to know what that actually meant, but if you just actually look up Intel's manufacturing sites, I think these are just like the factories that they make these types of wafers and chips, and D1 is, I think, one particular place. I believe it's in Hillsborough, but I'm not 100% on that. Okay, and so they use as I said, their existing sort of semiconductor technology, their fabrication facilities in order to make this kind of a particular chip. So it's a 12 qubit device that leverages, Intel's most advanced transistor industrial fabrication capabilities, such as extreme ultraviolet lithography. As we know, chips are getting smaller and smaller, and so as they want to pack more and more transistors into a chip like this, they need to use higher and higher wavelength in terms of lithography, because as you can guess, the shorter the wavelength of the lithography, the finer the detail that you can create on these chips. Traditional lithography, optical lithography, works with wavelengths somewhere in the 365 to 157 nanometer range, but then this extreme ultraviolet lithography is going down using wavelengths something more on the order of 10 nanometers. So using those, they can make these extremely fine structures. Contact processing techniques they mention, I'm not really quite sure exactly what that particularly means, but presumably these are all the other gates and contacts that you need in terms of making these chips. So in silicon spin qubits, information 01 is encoded in the spin up-down of a single electron. So your qubit in this case is an electron. So this, as we're going to see, it's a gate-defined quantum dot. And each qubit device is essentially a single electron transistor, and these types of quantum dot systems, the essential physics that you are relying on is this notion of a single electron transistor, which we'll get back to just in a minute. And then so the press release continues on, which allows Intel to fabricate it using a similar flow to that used in standard complementary metal oxide semiconductor, so CMOS logic processing line. Okay, that's pretty much all the technical details that they provide in the press release, so there's really not very much information there. Okay. Apart from the press release, there's also like a blog post and a bunch of things by like the director of quantum hardware at Intel, and this kind of tells you a little bit of the trajectory that Intel has been taking in terms of this kind of technology. So you can see in terms of their kind of stuff that they're actually putting out publicly, it's been relatively recent, right? They've listed a few milestones that they've got to. So the first one kind of starts in December 2020. Presumably they started way before then as well. That's the first time that they had some kind of tangible results in this. They're relatively a kind of a new player in terms of the publicly disclosed information, the kind of milestones that they've been talking about, something like this cryogenic quantum control chip, which is the outer infrastructure of this quantum chip that they're releasing now. And firstly, these are 300 nanometer fabrication milestones. So I think in terms of the publicly released material, there isn't that much to go on. However, if you just look up the publications by the main researchers that are involved here, you can find some publications which actually give you a much better idea of the real kind of technology that is behind this. So I'm going to focus on a particular paper that was published in March 2022, so this is already a year old. However, I think that this is pretty much the technology that they're dealing with. Specifically, this guy, J.S. Clark, who's the last author here, he's like the lead researcher, the guy that wrote that blog post, a couple of slides ago. I think this paper is a collaboration mainly with the Intel team and the people at the University of Delft. So this guy Van der Sijpen, he's a very big name in the quantum computing community. He does semiconductor systems. And so I think what's happened in this paper is that Intel made some of these chips and then they handed it over to the people at Delft. I think they both did some measurements on the system. They got back together and they analyzed it and they published this paper. Let's go through what this paper tells you. In figure 1 of this paper, they give you a device diagram. So this is already much more detailed than is actually in the press release. And this tells you what kind of physical system that they're dealing with. This is, as I said, a silicon-based system, and they have multiple layers of metallic gates and various other materials in order to control the qubits. The actual kind of physical device or the structure that we're actually dealing with is, the core of it is this fin formation. So on this picture here, in the top left here, you've got these two narrow fins. So they're about 20 to 70 nanometers thick, and there's two of them. One of them contains the qubits that we're eventually going to be using for the quantum computer, and the other one is eventually going to be used for the measurements. And what happens in the system is that, okay, so this is actually showing some of the process in actually making this particular system. But after you deposit various other materials, such as silicon dioxide, so this is a standard kind of insulating substance. The rest of the purple parts are silicon. You deposit various other gates on the top of this, and what this does is to create regions of potential maxima and minima, right? And within the fins, so the qubits are going to be defined by electrons that are going to be inside each of these fins. And by putting gates, you can chop up the fins in various little pieces, and each part of the fin is going to be a region where the electron can live, and that electron is trapped there, and then you can do some control on the electron in order to make your qubit, right? Okay, so the bottom stuff here are all the gates that you need in order to control the system. So, one thing that they are quite, I can tell, proud of in terms of this paper is that they can really mass produce these qubits to a very large scale. In that 300 millimeter wafer that was already there in the press release, they can make sort of 82 unit cells. So I think what this means is 82 different copies of the system. So in a way, 82 chips eventually. And each one might contain anywhere between 10 or more numbers of qubits. And so eventually the total number of qubits that you can make in a single wafer might be somewhere in the region of 10,000. Now, of course, these are not all interconnected, they're just duplicates, but then the point is that they can mass produce this using their kind of semiconductor technology. And so this is one real advantage of this particular system. Another thing that they are extremely proud of, I can tell, is that they have a very high success rate of making these chips. So this figure here is a schematic of the 300 millimeter wafer that I showed you a real picture of a second ago. and each of these green squares, it would be like, say, one of these chips. And in one of their fabrication steps, what they can do is to, with very high probability, make a working chip, and by it operating correctly, or yielding, as they say, what it requires is that the fins can actually turn on. That means that it can conduct some current. Individual gates on each of the fins can control this current, and then the ohmic contacts and the gates are not leaking, which means, I guess, that there's a high efficiency in terms of the current that you can put through one of these fins. They make a point in the paper that not a lot of people actually say what their success rates are actually in terms of making this, but at least in their system, it's very good. The kind of measurements that they do, your kind of classic quantum dot, Coulomb diamond kind of experiments. So this is a good place to talk about the physics of the single electron transistor. So in a single electron transistor, what you have is, just like in a regular transistor, you have a source, drain, and then a gate. But the difference to a standard transistor is that you have everything working at the single electron level, right? So in a transistor, if you apply a voltage to the gate, then the current can flow, or if you take the voltage off, then the current stops. That kind of physics is operating at the single electron level. The way that you picture this kind of thing is that in the diagram on the left here, you've got the structure with the two barriers, and then you've got discrete energy levels, just like you learn in elementary quantum mechanics. When you solve the square, you have discrete energy levels. And on the left and the right, you've got some unconfined area, and there's a whole bunch of electrons out there which you consider to be filled up to some Fermi level. And so the point of this kind of thing is that if you control the position of these energy levels up and down, then you can have a regime where electrons can either flow or not, right? And so if the electron level in the quantum dot in the middle is just at the right level, then the electron can flow. But if it's in the wrong part, then the energy level is either too high or it's occupied by something and it's blocked, it can't flow. By applying a physical voltage to that quantum dot, you can control the energy of these levels in the quantum dot, and then that either allows current or doesn't allow current. And these Coulomb crystals, the figure on the right that you see here, is the kind of thing that you see typically. And so as you increase the gate voltage, there are regions where you do see current or you don't see current. Okay, so that's the basic kind of physics that you're supposed to see in these systems, and indeed they do see this same kind of physics. And so at the single quantum dot level, you see these Coulomb oscillations, and everything works as expected. Now, they also do some measurements with a double quantum dot, and what you see here is that so these series of figures, what is different in these figures here is that it's raising like the potential barrier between a double quantum dot or relaxing it. So there's no barrier, and so there's just like a single quantum dot. The different figures control the barrier between two quantum dots, and then the vertical or horizontal axis are similar to the previous figure that I already shown. So that is why you see these kind of Coulomb oscillations, say on the right there. That's on the right hand side figure where you only have one quantum dot effectively. You just see standard Coulomb oscillation. But on the left, where you see when you have two quantum dots, you have these kind of so-called triple points, and this happens when two levels align, so that like an electron can hop like continuously between these two quantum dots and then end up at the other side. And that only happens at some very special conditions, and the kind of signature of that is this sort of, I don't know how you call it, this kind of square lattice or diamond kind of lattice behavior. Okay, now what's important to keep in mind here is that actually this is the only 2-qubit experiment that they do in this whole thing, okay? And the rest of everything that they do is all 1-qubit stuff, and this is not a real kind of 2-qubit kind of experiment, to be honest. It's, yeah, sure, it's two quantum dots combined, but then there's no 2-qubit gate fidelities or anything like that. It's just, we're just confirming some existing physics that we know should happen in, say, these double quantum dot systems. Okay, now continuing on, the rest of the stuff that they do is to characterize the qubits and to look at how do you do things like readouts. And if you remember the other fin structure that they have, what that can do is to sense the presence or lack of presence of an electron in the qubit system. And then so the figure on the right, by varying the voltages on the qubit, you can successfully determine whether there's an electron present there or not. And so that serves as your kind of measurement readout of the qubit. So another kind of measurement that they can do is that if you apply a magnetic field, you can do a spin selective measurement. So not only can you just detect whether there's an electron there in the qubit there or not, you can also figure out what its spin is. How they do this is they apply a magnetic field. This creates a Zeeman splitting between the electron levels, and by coupling it to this contact, they can do this kind of spin select readout, so they can figure out whether it's a spin up or a spin down. They can work out things like parameters of the qubits, T1 times, that's like the relaxation time. So to work out T1, what they do is they do this three-stage process of they empty the dot, inject the dot with a particular spin, wait for a particular time, so that's the horizontal axis here, and then read out the spin and see whether it's survived that wait time. And so they have a T1 time of about 1 second, which is considered quite a long time. It's very good for a quantum computing system. And they can also measure T2 times. Now these are much shorter. They're in the region of microseconds, and they do this with Ramsey interferometry. And but they can still detect coherence in the system. They control the qubits using oscillating magnetic fields, and so they have these strip lines that they can put an oscillating magnetic field around a qubit, and then that drives the qubit, and they can see these Rabi oscillations. Now finally, they also do some randomized benchmarking types of things, and what this is trying to test is after you applied a bunch of particular Clifford gates, so these are gates that are things like Pauli gates or Hadamard gates, things like this. Now, can you get back to the original state after you apply a particular sequence? So say you apply a sequence of X Hadamard, Z, X Hadamard, that should go to some more simpler gate which should invert that sequence, and you should be able to do that in one step. And how successfully can you do that? It's a benchmarking scheme, and this is how they work out what their gate fidelities are, and they claim that their gate fidelity is around the 99% regime. Okay, so that's the quick rundown of a paper. Obviously, I didn't go through all the results. I think it gives you a bit of a flavor of what this kind of system is capable of. I think my take-home message here is that it seems to do stuff at the 1 qubit level reasonably well. I don't really see much evidence for 2 qubit kind of operations, and I think this is why still it's a research grade chip. What they want people to do is to go out and further develop the system. What do you guys think?
Does the chip work at room temperature, or does it require like cooling?
Yeah, so, sorry, I forgot to mention that, but this whole thing needs to be put in a dilution refrigerator. This probably works at something like 10 millikelvin. Yeah, so you're probably not going to be able to have one at home.
What are the decoherent sources for such systems?
Semiconductor systems are pretty noisy. They have, even in this very sophisticated kind of semiconductor fabrication, and I'm sure they've got the world's best kind of samples, it's solid state. It's not like it's a vacuum system. It's always got noise, and so
lattice defects.
Sure, yeah, exactly. Sort of lattice defects. As much as you can, the crystals are just about perfect. They are always present, and I don't know, phonons, all kinds of things. Yeah.
How does it compare with superconducting qubit? Because I have some previous research experience on superconducting resonators. I'm curious which one is.
Oh, I would say that at this point, there's no competition, actually. The superconducting qubits are like way better in terms of, we haven't really seen a very convincing 2-qubit gate here. Superconducting qubits can do 2-qubit gates at something like 99% fidelity, and they can make okay, I mean, they have 500 qubit machines or whatever, but then actually probably only 9 of them coupled together very well. But still, that's a lot more than what we're seeing here, right? So that's definitely the leader, and ion traps are also up there. These are the kind of traditional leaders, and they're still the leaders. This, you got to say, is like a kind of a new kid on the block in terms of quantum computing.
You mentioned recently 12 qubit is the I think starting point they have achieved, but still like IBM and other research companies, they already showed more than 12 I think in the latest.
Yeah, this is the thing, like it's 12 qubits, but if they don't have a very good 2-qubit gate, then it doesn't really matter. It might as well be 1 qubit. Okay, yeah, they can do some 2-qubit-ish stuff, right? Like with the 2 double quantum dot resonant tunneling kind of stuff. But that's not a 2-qubit gate. That's just some 2-qubit kind of physics. Until they start doing actual entanglement and showing quantum volumes and stuff like that, like you can't really even compare them actually. Yeah.
That brings me to another thing. Like this quantum volume you just mentioned, do I expect to see it here, or I think it was something coined by IBM or Google? Is it the name of Google?
IBM,
Yeah.
IBM.
Yeah. So now, does it mean that everybody have to use that as a standard?
I have to, but it's reasonable. Quantum volume is the largest D depth qubit
Qubits you
that you can do with D qubits, right?
So, but these guys know now is wafer, right? It's flat. Or where is the depth? Or maybe you stack flat wafers, or
Sorry, where's the what?
their own technology is flat.
Yeah.
He's holding it though. It's
Oh,
a
okay,
wafer.
sure, yeah.
So does it mean you stack it to get the volume, or you look at 1D flat surface?
It's always going to be like, I think, a 2D thing, yeah. 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 Okay. So maybe they can do 3D stuff, but I think it's too complicated. They already are doing some sort of 3D-ish structures in terms of this, but that's just in order to make all the gates and the control lines and everything like that. To have multiple layers of qubits is, I think, that would be insane. So,
They didn't really do any tests. What can he really do? I think that's what they want people to do. Go in and do it for them, not necessarily them doing anything with it. I think that's what I understand when I read the press release, because Google claimed something, IBM claimed something, but they just released their chip and that's it. So
yeah, I don't know. I don't think it can do a whole lot yet, really. It can probably do 1-qubit operations, okay, but beyond that, I think it's still very much research kind of level thing. Stuff is become pretty popular. Like we've done 2 or 3 videos on silicon, right? So it's really picking up.
If they get it right, the technology is already there. All these things we use are silicon-based or transistor-based. So
Okay, all right. That's all we got. Thanks for watching, and we'll see you for the next video. Bye.